Hello guys, welcome back to the Data Structures and Algorithm course brought to you by Asha Akanksha Foundation. So in this lecture we will discuss about merge sort and quicksort. These are the two sorting algorithms which we most oftenly used in data structures and algorithms. There are multiple other sorting algorithms also, but in general we use these ones and you would encounter questions of these two only. So now first we will discuss about merge sort. So the basic idea of merge sort is that we divide the array into two, we sort the two sub-arrays and we make a function of this. Don't worry about that, we'll discuss it later. And then we will merge the two sorted sub-arrays into a single sorted array. And this is done recursively. Sorting the sub-arrays is done recursively, that is divide into sort merge until the array has a single element, which is the base case of recursion. And if we have a single element, so we just return that because a single element is sorted on it in its own. So let's take an example that take this array as an input array. So first we will divide this array into two halves. So this is one half and this is the another half. So we have left, we will make left sub array, then we will make right sub arrays. These are the two half which we made by splitting the array into two. And then we recursively split the arrays into two halves. So if we split the or left array into two, we get this, and if we recursively do it, we will be left with this two subarray in the final split in the final split method. Now, since we have a single element, we will return that only because a single element is sorted in its own. So and then we will merge this returned elements into a sorted array. So this is how it will looks like. We're gonna discuss all the algorithms which we are stating here just literally and just verbally, and mm, we'll discuss those algorithms and the logic behind them in the later slides. All right. Similarly, we divide and merge the array. We get the sorted array, and then uh, in the final attempt we will get the whole sorted array, and then we will return this array. You can see over here that we did the same thing with the right half which we got over there. We split it into two halves till we get a single element, and then we return these elements and merge these arrays into sorted arrays, and then we'll get the final answer. So over here, sorting 8 elements required 7 merge steps. So to make merge sort to make merge sort more interesting, I have some YouTube video links which you can see to uh, clarify concepts more clearly and visually in a fun way. So I will highly recommend you to watch these videos through these links. I will also put these links in the description box below. So I hope you have watched this video by now. Now we'll see how the merge sort works behind the scene. So merge sort needs a helper array to merge two sorted arrays. As we have discussed that we have to merge two arrays into a sorted array. So this is the merge sort class which we are making. We have this A as the input array and these aux as the auxiliary array. Alright, so the other step which we do in the merge sort is recursively keeps on dividing the array in equal parts. So how can we divide the array in equal parts? We find the middle element of the array, and then we recursively call the merge sort function from the lower index to the middle element, and another merge sort recursive function from the next to middle element to the higher element. So this is the function, and yes, if the base condition for this merge sort recursive function is that if the lower index surpasses the higher index, we just return from the function because it is not possible in a normal array to have lower. It is not possible to sort any array which has higher lower index and lower higher index. So we just return from there, and in the final step we merge both the arrays to get the sorted arrays. Uh, we merge both the sorted arrays to get the final answer. So this is how the recursive function of merge sort looks like. So now we'll see. Uh, now we have to copy A into auxiliary array. Pointers are set for two sub auxiliary arrays and the array which collects elements after merging. So this is the merge function which we have made. We pass few parameters like lower index and middle index and higher index. So we copy the contents of A into the in this auxiliary array. Then we have initialized ijk as the lower, middle, and uh, lower element. So we then make a while loop to uh, transfer small of the two elements from the subarrays to the merged array. So this is the while loop. In this while loop, we make sure that the starting index is less than the middle and the jth and j variable is less than the highest index which we have passed in the function. So if since we have all the content of the input array in the auxiliary array, check that if the uh, if the element at ith index is less than jth index, that means this that means we should put this. That means this is the smaller element, and we should put this element in the final array, and then we'll increase the index. Otherwise, if the element at ith index is less than the jth index, we will push the jth element in the array, and then we will increase the k variable also, so that the index of the final array also increase to put the element while merging. And in the final step, what we do is, if all the elements of one subarray have been put in array A, remaining elements of other arrays are simply copied into it. So in the final step, we'll check if all the subarrays are copied into A, because in this condition we have both our indices should be in the our indices should not surpass the length of any of the two arrays. So it can happen that one array has been that we have processed a whole array. We have processed first array fully, and we are left with some elements of the second array. So then we simply copy those elements of the second array to the final array. So this is the code of that. Alright, so now we'll discuss the time complexity of merge sort. So like binary search, array is divided into two parts at every stage. So work done appears to be of order of log n. Alright, this is a pretty simple thing. At every state, each element of the array is copied and may be processed. So this is bound to be of order of n. So the overall time complexity of merge sort is order of n log n. So we can also make a recurrence relation of the merge sort time complexity. So T of n is equals to 2T of n by 2, because we are calling merge sort function on two halves, and then we have merge function which takes order of n time complexity. So this is the recurrence relation which we get from the merge sort recursive function, and the base condition is that if the lower index surpasses the higher index, we just then return, so T of 1 is equals to 1. So if we solve this recurrence relation, we'll get that the time complexity is order of n log n, as we have discussed in the previous slide from intuition. So we can prove the time complexity through this recurrence relation. So now, since we have discussed on all the major points in the quicksort, now we'll move forward with the quicksort algorithm, which is better in average than the merge sort. So let's see what is the basic idea in sorting an array. We choose an element x in for Quicksort. We choose an element x in the array's pivot, and we place that um, pivot in A such that all the elements to the left of the pivot are less than the pivot, and all the elements to the right of the pivot are greater than the pivot. So we make sure that the pivot is now in its proper position in the final sorted array, and then we recursively sort the left and the right halves of the pivot. So I guess you are able to follow me and get the basic idea of Quicksort. So let's try to break down into steps. We first choose a pivot element from the array, and then we start from second element and keep on moving towards right till an element greater than pivot is found. And similarly, we start from last element and keep on moving towards left till an element smaller than pivot is found. And as soon as we found both the and as soon as we found both elements, that is, one is element greater than the pivot and one is element smaller than the pivot, we exchange these two elements so that they land in proper part of that of the array. So this is a kind of divide and conquer strategy, because we are recursively calling the same function on a smaller pass. So a major concept in Quicksort is partitioning an array. What do we mean by partitioning an array? That means we have to place the pivot in its correct position of sorted array. So let's say that pivot, we have chosen a pivot of the pivot index as 0, so means 40 is our pivot, and we have to place 40 uh, as in the place of a sorted array. Alright, so we start from the lower index and the higher index. We keep on uh, so so we keep on going uh, till element at too big index is less than pivot. Uh, this is the point which we have discussed in this point, that we have to move towards right till we are getting elements smaller than the pivot, and we will move to the left till we are getting elements greater than the pivot. And at the end of the while loop, that means that we have encountered an element that is greater than the pivot from the first loop, and from the second loop we got an element which is smaller than the pivot. So in the last we just swap these two elements to place them accordingly, and after getting from this while loop, check if we check if the lower index is greater than the two index in bigger index. That means we have met the boundary condition, and we just return. And in the last we swap the pivot with the smaller index, because that is the index of the last smaller element than the pivot, and pivot should be placed after that in the sorted array. So that's why we swap that pivot from that element. So after partitioning our array, this array would look something like this. We have 40 at its correct position, and all the elements on the left of the 40 are less than or equal to 40, and all the elements right to the 40 are greater than 40. So this is how partitioning works. Let's try to understand the partition algorithm with some other examples. So let's take this array as the input array. We'll examine the array from left and find the element not in place. So we first have to place 45 in its correct position. We move to right from first index to find element that is not in place. So that means that it is greater than the pivot. So we encounter with 82, which is greater than 45. So we stop over here, and uh, now moving to the second step, we start from examine the array from the right and find the element which is smaller than the pivot. That is the element which is not in place. So in this array, we will encounter with 9, and then we will exchange 9 and 82 uh, with the respective positions. So that they remain in place. And then we recursive, and then we'll do this method again and continue the process. So we move right from 9 till we encounter an element greater than 45. So we encounter with 60, and from examining the array from right, we encounter with 40 since it is less than the pivot. And at the last, we exchange these 60 and 40 to make them in their to keep them in their correct place. So how long this process goes on? So this process goes on till our lower index is less than the higher index, because if this doesn't happen, that means we have sorted the whole array, and we just return from that loop. So as I said, over here, since L and R have met, so we return from the function. So the overall algorithm of the quicksort was partition the array, get one element in right place, and then sort the left subarray and then sort the right subarray. So this is a pseudocode of the algorithm for partitioning array. We initialize first index, we initialize last index, we select a pivot, and in the while loop we keep moving to right till we find an element greater than pivot, and we start from last element and keep moving to left till we find that element less than pivot, and we check if the ith and jth index have crossed or not. If they have surpassed each other, that means I is greater than j. If that's the condition, we just have to return from this while loop. Otherwise, we just have to exchange the ith and jth index so that they go in their correct respective positions. And in the last, we have to exchange the pivot with the exchange the pivot with the element, exchange the pivot in its proper place in the array, and we output j as the partitioning point. This j is the this this j gives us the last element that is less than pivot. So that's so that is all about partitioning algorithm. I will request you all to watch this YouTube video, which is to get a good understanding about Quicksort. So the overall Quicksort function look like this. We over here we partition the algorithm. Over here we just break the mm, array into two and select a pivot, and then we do partition. This is all partition algorithm, and over here we recursively call quicksort function for the left half and the right half. So this is an example. This is an example to fully understand the above algorithm and code. I will request you all to pause the video and solve this example on your own. So now we will analyze the time complexity and space of Quicksort. So assuming that keys are random and uniformly distributed, the best case running time complexity for Quicksort is order of n log n. Mind it, this is the best case and not the worst case. So the worst case running time of Quicksort happens when partition splits the array into two subarrays with one subarray of size 0 and the other subarray of size n minus 1. one subarray of size 1 and another subarray of size n minus 1. So the depth of our recursion tree would be order of n, and number of accesses per partition is order of n also. So keeping this in mind, our worst case time complexity becomes order of n square. So think about what we can do to avoid this worst case. I would request you to think upon this idea once and pause the video over here and and think about what can we do to avoid this worst case time complexity in Quicksort. So I think you might have thought about this. Now we'll discuss what we can do to improve the worst case time complexity of Quicksort. So to improve the worst case time complexity, we just pick median value of 3 elements from the data array. So the median value would be of 0th index, n by 2th index, and n minus 1th index. So I will not gonna discuss the mathematical proof of this because that would go beyond our course scope. So I'll just discuss the result over here, and uh, and I'll not prove it right now. So this is the result which we got, that if we have to pick the median value as the pivot in the quicksort to avoid the worst case time complexity. Alright, so I hope you must have understood all both the sorting algorithms, merge-sort and quicksort, which we have discussed in this video. In the next video, we will jump to the linked list data structure. So if you have any questions regarding this video or any other concept in data structures and algorithms, you can comment down below, or you can also reach out to us at our instant Facebook pages. So till then, stay safe, happy learning, and hope to see you in the next lecture. Bye bye.